Hey, I'm Zhang from Georgia Tech, and I'll be talking about our paper Paprika Private Online Force Discovery Rate Control. And this is joint work with Gautam Kamath. He's at the University of Waterloo. And my advisor, Rachel Cummings. She's at Columbia University. To give the background, think about a model where we have a scientist here, and she wants to test multiple hypotheses on a particular database. And she gets back p-values. And she was very excited to find an interesting but rare discovery when the p-value is very small. But is this discovery really valid and reproducible? Sometimes the noise can be mistaken for a signal. When adaptive testing multiple hypotheses, the probability of such false discovery increases as more tests are performed. The problem of false discovery control is to design a procedure that takes in p-values of all hypotheses and decides which to reject. And this procedure should control the FDR to be below than its threshold, while maintaining high true positive rate. In many applications, the dataset may contain sensitive personal information, such as the GY study and the clinical trials. So we need formal privacy guarantees for FDR control algorithms. Formally, the FDR is defined as the expectation of the proportion of the false discoveries out of all rejected hypotheses. Unlike previous methods that focuses on the offline setting, we are looking at the more challenging online setting, where we have p-values arrive one at a time, and we must make rejection decisions immediately before the next hypothesis arrives. And those hypotheses can be adaptive, and it's not known how to do it online privately, and this is what we are going to solve. We use differential privacy as our privacy notion, and informally, differential privacy bounds the maximum amount, and one person's data can change the distribution of an algorithm's output. And formally, we see that an algorithm that is absolute delta differentially private if for all pairs of neighboring databases, then differ in only one person's data. The distribution over the output must be approximately the same, except with a small probability delta. And we give a differentially private online FDR control algorithm called Paprika. And the main idea of Paprika is combining two subclasses of the generalized alpha investing rules, the log++ and saffron, with a private mechanism sparse vector technique. However, the combination of these tools is far from immediate, and several algorithmic innovations are required. First, the threshold updating rule is similar to the log++, so that the thresholds do not depend on the data. Second, we have to incorporate dynamic thresholds to match the alpha investing rule, and show these dynamic thresholds do not affect the privacy guarantees. And third, we are adding noise that scale with a multiplicative sensitivity, and this sensitivity notion was proposed specifically for p-values, as p-values tend to have high additive sensitivity. And then we shift the threshold, and we compare against the p-values weights to accommodate FDR as a novel accuracy metric. And finally, the candidacy indicator step from saffron cannot be done privately, and it requires new analysis for both privacy and accuracy. And we show Paprika provides alpha delta differential privacy, and it controls FDR to be below than alpha plus delta t for testing t hypothesis if p-values are independent. And this delta is cryptographically small, so delta times c is still tiny. It can also control a slightly weaker notion of FDR called MFDR if p-values are adaptive under the null. We also have a bunch of empirical results in the paper to empirically evaluate FDR and the statistical power, which is a true positive rate. It suggests that our algorithm is good for practical use. And for more details, please check our paper online. Thank you.